We'll start in 5 minutes. Wait. Don't start recording. Some time. On behalf of Wilson College and Indian Association of Physics Teachers, Mumbai Sub-Regional Council, we have organized this particular lecture series. It is two lecture series today and tomorrow, and I welcome you all. We have here our head of department, Professor Shekhar Devdar, Sir Michael D'Souza from Wilson College, and our host is Merita here. Uh, we have with us from IIPT, Professor Rekha Ghorpade, Madam, who is the General Secretary at the Central EC. Also have with us the President, Mumbai Sub-Regional Council, and other members from Mumbai Sub-Regional Council. I welcome all of you from Physics Department, Wilson College, and I request Rekha Ghorpade Madam to speak few words about IIPT and about the program, about our collaboration, and then I will talk about the program and I will introduce our speaker.
Thank you, Professor Mahesh. The respected speaker today, Dr. Vishwajeet Swain, Principal Wilson College, the other staff members from Department of Physics, my colleagues from IIPT, and the other participants, those who have joined the course, all the members present here. I welcome you on behalf of my personal behalf and as well as the Indian Association of Physics Teachers. Indian Association of Physics Teachers is a 40 years old teachers organization established in 1984. This particular association was established by the very like-minded people led by Professor D.P. Khandelwal, and this was a platform provided to the teachers and students to upgrade the physics education throughout the country. Now we have added lot of flagship programs. One of them is, of course, the national standard examinations for high school and plus two level students. Now these examinations are the only examinations for the gateway to the international Olympiads that most of you probably must be knowing about it. And I can see Professor Varun Bhalera, who was also our astronomy Olympiad student, I mean the medalist here. And there are various competitions. I will not take much of a time because we are already late. You can visit our website. I will post the link for the website in the chat box later. You can visit the website and come to know the flavor of the programs and the other the platforms things available for the teachers and students throughout the country. I welcome all the teachers present here and the students to become a member. We have now 10,000 plus members all across the country and also overseas. We also welcome the mentors. Recently, we have signed the MOU with Wilson College. Actually, Wilson College has become our nodal center for IPT activities. We have really been, I mean, we are really thankful to the principal and the management of Wilson College for providing us a necessary infrastructure. Up till now, we have conducted 3 summer schools in Wilson College and some other colleges also. Our summer school started 9 years back in Wilson College, and Professor Mahesh Shetty is the key person and he's always the coordinator for the summer school. We have a lot of beneficiaries from the summer school and this is still going on for last whole 9 years also. Now here, I also would like to invite the students to participate in IIPT activities. When they go back to their institutions, please try to talk about IIPT and the other activities. Try to participate. You will get the national platform to explore yourself and also to showcase your talents in various competitions conducted by IIPT. We have 24 regional councils, each council in one state. And also we have 7 sub-regional councils, like 5 are there in the Maharashtra itself, so that we are reaching out to the corners of every corner of the country. And our motto is reaching the unreached. And therefore we are reaching through our regional councils. uh, to the community, IIPT teachers and students community. We conduct various workshops, seminars, and other programs to upgrade the physics education also. So here I once again welcome you one and all, and I request you to join the hands with IIPT. Before I close down, regarding this course on astronomy, I really appreciate the initiative taken by Professor Mahesh Shetty and the other team members to start this kind of a program, which is an introductory program in astronomy and astrophysics. Of course, astronomy is the focus of this program, and the people, those who are not the physics students, also can join this program. This is for the very common people, people who do not understand physics or the other things. They can enjoy this program. And for I do not know, but must be for 7 8 years. Mahesh sir is running this program in Mumbai, and the students who have joined this program have benefited a lot. And those who have joined now for this program, I'm sure you are going to get a lot of information, lot of fun, and lot of enjoyment through which you are going to learn the basic concepts. First of all, very important is how to look at the sky is the main thing, and which I think you are going to get through this kind of programs. I'm sure they must be having the night sky observation programs also included in this program. Today is the inaugural program. I welcome wholeheartedly Dr. Vishwajit Swain for giving this inaugural lecture from IIT, and I wish everybody a very good luck. I am sure all the participants are going to have a fruitful time next few months and enjoy the program. And I wish good luck to Professor Mahesh Shetty and the team for the whole program. Thank you so much for giving me the opportunity to interact with you all. Thank you.
Thank you, madam, for your kind words. Uh, we have, okay, without having further ado in the uh, program, let me quickly introduce Mr. Vishwajeet. Vishwajeet is the final year PhD student working under Professor Varun Bhalerao from IIT Bombay, and his research area is in time domain astronomy, regular monitoring and advancement of Growth India telescope. Growth India telescope is the only robotic telescope in India, and if those who want to know about more about it, okay, in our last winter school, uh, Wilson College as well as IIPT in collaboration, Professor Varun Bhalerao had given a long lecture on what is this Growth India telescope, a detailed but introductory lecture on this particular telescope and the kind of things they are going to observe in that. So Mr. Vishwajit is working on that. He is also doing transient studies like gamma ray burst electromagnetic counterparts of the gravitational wave events, and he's closely working in collaboration with Caltech for the search of transient and their physical interpretations. So when I asked Professor Varun Bhalerao that because he has been always helping us in these kind of programs, and I asked him that now under NEP, our students are going to do field projects. So those who are interested in astronomy, they can get access to some kind of data which is available in online portals, online various surveys. So is it possible that can someone give a lecture? And he immediately said, which he is doing great things for our students. So he sent me his contact, and that's how this lecture has been possible. So over to Vishwajit. For today as well as tomorrow, we are going to explore how to get these data from various archives which are available. So I have already requested Mr. Vishwajit that he will start from scratch in a sense that people may not be aware of how to get the data and so on. Of course, once the data you have received, what to do with it for that astronomy is required, and those things can of course be discussed and can be learned in different series of lectures. So over to Mr. Vishwajit.
Hi all. Yeah. Thanks committee to giving the opportunity to give the talk here. And yeah, I guess so. I will like to cover here the treasure hunt in the sky. So basically, the mainly about the archival data in optical and IR. and how the people can discover the new physics and new objects, which is very interesting to us. For example, in the 2023, there was a discovery like when the stars like a sun can engulf a planet around it. It's not always like a star have to be die and then engulf the planet. It was a different case where the due to the loss of the gravitational waves energy, and then the orbit come closer, so the planet come close to the star and then engulf it. So these type of discoveries have been done, and then can be and then it was so first discovered by the ZTF data, and then from the archival data, they found that there are the more such types of event which was happened before, and then especially in the higher band, it was a rise by the factor of 5 in brightness. So yeah, so I will try to give the brief introduction for the how to get the data and do the science, and then what are these data tell about, and what are the structures, and then where from where service and surveys and uh, sources you can get the data. Okay, let's start from the outline. So in first, so today lecture I will cover few of the basics so that you can have what is the column, for example, the columns are present in the catalog. So what are they? What do they mean, right? And then accordingly I will go through the from the coordinate system to the HR diagram. And HR diagram is also a good example of the archival utilization of the archival data, from which we now know there are different classification of the objects like supergiant, main sequence star, and white dwarf. And then I will try to go through the archival data which are present and mostly used, and what I use basically. So again, so this is a some limit number of archival data I will discuss, but there are more lots a lot of archival data are there, and then services are there from where you can get more data. So, but we will try to complete few one, and then and give the opportunity for the student to explore more. Yes, and then in the end, I will try to show the how to utilize the DS9. I guess most of the amateur astronomer use that. So it is tool to imaging the images taken by the telescope. And in the lecture two, which is tomorrow, we will try to revise few things and then give you the science cases, the flavor of the science cases which has been done from their level data. And then again, we will try more with the Python coding, and TopCat is again a tool which is an interactive tool for uh, to plot the HR diagram and plot many things from the Caval data. Okay, so let's start from the basics. So in the basics, I will discuss about coordinate system, distance, magnitude system, filters, and HR diagram. So first of all, we will talk about the world coordinate system. So like latitude and longitude of the Earth system, coordinate system. So we have a celestial world coordinate system for the celestial sphere. So sky we assume a celestial sphere where we should have some coordinates so that we can point where the star is. And then this coordinate system, the RADEC especially is the world coordinate system, so that it's fixed coordinate system. So if the star has some RADEC, then it will not change with the time. So and again, there are the other coordinate system, but they change with according to the observer. So I will not talk about that, but mainly we will focus on the RADEC. And then again, for the RADEC, as mentioned, that is measured in hours from 0 to 24, or say the from 0 to 360 degree, and 1 hour is equivalent to 15 degree. And then again, every coordinate system has a reference point. So again, in this case, RA has a reference point of vernal equinox. So I will talk about the vernal equinox. And then there is a declination which is going from 0 to 90 and minus 90 from the equator, celestial equator, and it's coincide with the equator of the Earth. And again, the reference plate is the celestial equator, and then these type of conversation are we are using for in the telescope to point any object in the sky. So I would like to show two things. So this is the interesting simulator I found, and then I have linked it in the presentation. And again, I will share that presentation with you guys, and then so that you can later check these things and explore more. So here is the example, and this is the vernal equinox. Vernal equinox is the point where okay, let me check. It is. Sorry, my clip is not. Okay. Anyways, uh, somehow my clip is not. Yes. Okay. So yeah, so this is a ecliptic plane, and this is something Earth is rotating around the sun. Right? If you can assume that you are on the Earth and then you see the sun, so sun is rotating around the Earth, and that plane we called it ecliptic plane. And then there is a intersection between the celestial equator and the ecliptic plane, and this plane is indicating the motion of the sun across the year. So at this intersection, it is a we call vernal equinox, and it is around 21st June, where the night and equinox means where the night and day time are equal. And this we the astronomer take as a reference point for the RA, and then you can see that if I in from in this position, it's a zero RA deck, and then from going to the rightward toward the east direction, it is increasing and going from 0 to 24, right? And then the declination is again from 0 to 90, and then you can see that going above is up to 90, and then going down in the south is up to minus 90. Okay, and let me come back to the yes. And there are other software which is Stellarium, and this is quite useful. And then I think many of you already use it uh, for the fun, I would say, and then to observe the sky with a small telescope. And then here the good thing is you can see the sky, and then according to your position, it is taking the position of the uh, Mumbai, and then we can see that with the time how the sky is evolving with the uh, time. And then in there we can see what are the objects are visible, what are the planets are visible, and it is also showing few of the satellites there. So it's just a cool uh, software to utilize. And then let's jump to the distance. So distance. So in the astronomy, we calculate the distance with a number of methods, but I will talk about here for the main two method, which is a parallax and spectral analysis. And so parallax method is something like it's used for the to calculate the distance of a nearby object. And then since the background, the distant object are at very large distance, so when you view the that nearby object with a telescope at different position, like it here is example like at one end of the orbit, and then other part is one end of the orbit, and then say other part of the orbit, and then from there we can see that due to the nearby object being with respect to the big background stars, so they form a parallax angle. And then basically it's like this is a show of the example, the images. So in this example, you can see that there are the background shot, but that nearby object visible at one of the position here, and then in another image it is positioned at a uh, different sky. So and then from there we can calculate the parallax angle, and then using the sorry using the parallax angle we can calculate the distance in per second. So yeah, So while we need, so the Gaia is, for example, the survey which observe mainly in the galactic plane, and then they are also calculating the loss of the parallax angle for the most of the stars which are present in our galaxies, and then finding the accurate measurement of the distance of that sources. And then also parallax angle we can measure up to, I guess, 100%. But yeah, in the on using the ground-based telescope we can measure up to 50, but using the satellite we can measure up to 100. But yeah, for the distant objective we can't utilize the parallax method because distant objective will not show much variation in the position of the source. So yeah, so for that we utilize the spectral analysis. So we took the spectral images, and so it's a little different. So it's a different from the photometric. It's a spectral images are basically the distribution of the intensity over the different wavelength. So to what wavelength, so at different wavelength what is the brightness of the that source. And yeah, from that I can show the one of the example here. So, for example, this is a supernova, and so one of the observatory took the uh, spectra, and then here you can see they found that the redshift. So again, the redshift is again related to the we can calculate the luminosity distance from the redshift, and again we in the astronomy we talk distance in the terms of the redshift. More the redshift, more is the distance, and again these redshift are due to the expansion of the universe. So yeah, here we can see that they found that this source is at the redshift of 0.0088, right? And then from there, how they found, I can show you, for example. So these are the spectral lines you can see, and then there are the absorption and emission going here, right? And so if I change this redshift to the zero, we can see that this absorptions line, which is supposed to be at the peak, it is shifted little bit, and this shift is because actually due to the redshift. And so astronomer usually take multiple emission lines, and then as mentioned here, the from hydrogen to the metals, right? And then in the finding the best redshift which can give the exact emission lines. Okay, and I guess I should show also the how the spectra work. Let me show you. I think that would be nice. So this is the example of, for example, let's say, yeah. So yes, for example, this is the spectrum, and then you can see the continuous spectrum, and then there is a absorption lines, and these are the absorption line is due to the absorption of the photon by the outer environment from the inner one, and then if there is a so since universe is expanding and then your source is going away, and because of since you and you can correlate it with the Doppler shift like that. So since the source is going away from you, so there is a rest shift. So your a wavelength which was should be observed, for example, 500 nanometer, it will be observed at uh, 510 nanometer, something like that. And then because of that, it's red shifted. And then from the source properties, we know that its emission should be at this wavelength, and then it is showing at 510. So we put the shift parameter and then take it back to the 500, and then that's the way we calculate the shift. Okay, let's move to the next part. Apparent magnitude, and so it's a basically a magnitude system. So in the astronomy we measure the brightness of the stars in the form in the terms of magnitude, and then it's a logarithmic scale basically, and then here you can see that it's defined as a magnitude equal to minus 2.5 log of the brightness. And then here is an example. If we have a star, so for two different stars, and we want to compare the brightness. So in terms of the brightness, you can see that the ratio is something like, for example, the if the one of the object is 100 times brighter than the other, then their magnitude difference will be the 5. And then again, so 10 and then 20 is related to the brightness difference of 10 power 4 and 8. So in the astronomy, we calculate the magnitude system like that, and but with the um, okay, so there is another parameter which is absolute magnitude. I did not mention that, but let me show it. Okay, so there is a two type of magnitude. One is a apparent magnitude, and other is a absolute magnitude. And apparent magnitude is defined as a whatever the source is at its position, and whatever the flux we are getting, that will be the apparent magnitude. But the absolute magnitude is defined as when you are at the 10 parsec distance, but is a magnitude of that source. So here is a one of the example that's this is a 10 parsec line, and this is the Earth, this is the observer, and here is the sun, and then you can see the apparent magnitude of the sun is minus 26.5, which is very bright. But actually, if we take this sun to the at a 10% per sec, then its magnitude is 4.7. So if we so it's basically if we want to compare the star with the sun, then we should take all the source at the same position and then compare it. It should not be apparent because there is a chance that the star is brighter than the sun, but it is at a very large distance and then it is looking fainter. So that's why we compare it at the same distance, which is 10 per sec, and then the apparent magnitude at 10 per sec distance, we call it absolute magnitude. And yeah, there is another example is a Vega star, and then you can see that if its apparent its magnitude is around 0, and then if I'm taking at a large distance, and you can see that its magnitude increases. So again, in the magnitude terms, you can see that there is a minus of the log of the brightness. So more the magnitude, it means the fainter is the object, and lesser is the magnitude, it means the brighter is the object. Okay, and yeah, again, in the catalog, you will see the lots of the magnitude in different filters. I will talk about the filters, but those magnitude are the calibrated magnitude. So again, so people need a standard system. So again, so for example, Vega system is using the reference star. So from a particular reference, we can calculate the magnitude of other stars, right? And even the apparent magnitude. So if we are calculating the apparent magnitude with respect to a particular reference, then we call it calibrated magnitude. Why we need calibrated magnitude? Because if I'm saying that this object magnitude is 25 or something, if then the observer in the other country would also calculate the same value. That's why we require some common reference so that everyone can calculate the same value of the magnitude. So in the Vega system, the reference is Vega, and then in AB system, which mostly we are currently using, in most of the catalog, you will see the we are using the AB system, but the older one was using the Vega system. And then difference is Vega has spectrum, so its spectrum is not ideal. It's the spectrum of the black body or the star, so it's not good for the comparison with the other. So that's why the AB system introduced, which has a spectra of the flat spectra basically. So it is assuming that all the same brightness at all the wavelength. So this is something a little bit of advanced topic, but just need to be digest few things that we have calibrated system for which we will see in the catalogs. Okay, so we have now the filters. So different kind of filter are used by the different instruments, and then we require the filter because we have to calculate the color of the object, and we and in this way again. So if the some of the object is very brighter in some of the filter, then it is better to observe in that way, and then you can reduce the background because taking the uh, full white filter observation will introduce more background noise because your source at different wavelength has not much of the signal, but there is a more of the background, and then you are whatever you are collecting in the in the instrument is the more of the background in that spectrum. So that's why we usually use the filter, and so yeah. Example is the Johnson filter. Again, they are the white filter and they are very old. And again, so from the U, B, V, R, I. So U is the more to the higher frequency, or the we say view, and then R, I is the more to the lower frequency, and we call it red. And similar, so Johnson filter are the wide band filter. So there are more of the overlaps, and then they are wide. So that's there is a next filter which is a Sloan or there's JSS filter. So they are narrow band filter, and then it is again good for the color spectrum. And then in the near infrared we have a JHK filter. And yeah, so, for example, we let's say the Sloan UGRIZ filter. If one of the object is very bright in U band and faint in I band, then it means that object is blue, and then it has more of its temperature is very large. We will see in the lecture diagram. But yeah, so we call it blue sourcing. If the I band is more brighter than the U band or the G band, then we call it red. So its emission is mostly in the high wavelength. Yes, let me show you one more simulator. So I have included lots of this simulation link in there, and it's very useful to understand the things, the physical picture of the filters and all. Okay, so for example, here we have an emitted source, and let's say we put a filter here, and so this is the spectrum, and then we can see that again, so source has some spectrum. So this is a example of a spectrum where the you can see, so this is a black body spectrum, and then black body is a mainly defined by the temperature, and then we can see the changing the temperature is changing the peak in the spectrum. And then uh, we have a filter. So if we are using the for example, let's say if we are using here we use the Bezier filter. Let's say we are using the red filter, right? So then you can see that the resultant, the photons, what we are getting is multiplication of source spectrum into the filter, and then whatever we got is the observed brightness. And then if we are putting the U filter, you can see, let me put it back, put it this. So you can see the detection in the right center in the detection, the your brightness increase because this spot is very blue, has a very high temperature. Okay, so let's move to the next part, which is the HR diagram. I will talk about more about the HR diagram tomorrow, and mainly we will try to make a HR diagram from a given cluster. But yeah, so but today we will go through the basics of this. Okay, so HR diagram is mainly the Sheila brightness and the temperature relation. So, and then in the terms of the observational astronomy, we measure it in the different filters and then plot it. So, for example, as I mentioned, so the object can be blue or red. So here we are using B minus V, for example. So B is very bluer side, and V is overall the visible range. And then if B minus V is let's say B is very small, which means magnitude wise it's very bright, and then B is larger in magnitude wise, so it's uh, uh, fainter, right? And then B minus V will be positive, which means that your source is more blue side, and you can say it's hot, right? And again, so this is a good example where the people took all the data and then plot and then found that there are different category of uh, the sources. For example, there are these Yeah, green shaded region is the main sequence star. These are the giants, these are the supergiants, and these are the white dwarf. And then here you can see the green lines. They are indicating the radius. So this is the one solar mass. So again, so in the astronomy we usually uh, measure the thing with respect to the sun. So here the line is for the one solar mass, and then going above is increasing the radius, and going down is decreasing the radius. And then interpretation of this figure is example for example. So this is a white dwarf, and then you can see it's small in size, and then its luminosity is low, and then V minus V is also low. It means that it is cool, and then its luminosity is low, and then again size is very large. And as compared to the supergiant, here we can see that its size is very large, and but we can see that its temperature is going from low to high. So again, so in if there is a supergiant which has a low temperature, then how the it has very high luminosity. The y-axis is showing that how bright is the object, how luminous is the object. So that this is because of the radius. So again, so this part of the giants, blue giants, have lower radius as compared to the this part, and that's why in the end we are getting similar type of luminosity. And then again, luminosity relation with respect to R and temperature is L that proportional to R square and T power 4. Okay, and uh, so uh, yeah, so mainly here you can see that so y-axis is indicating the luminosity and the x-axis is indicating the temperature, and then the same graph can be produced with the magnitude and with the B minus V color. So basic in the observation we are actually calculating plotting between the magnitude and the color index. But yeah, in actual, if you know the if you know the apparent magnitude, and again, this type of cluster is useful to for example, Pleiades cluster. It's a cluster at the same distance. So if, whatever the apparent magnitude you are getting, it is coming from the same distance. So the this absolute magnitude will be the scale factor of the distance. So, but the relative brightness will be the same if we are plotting the apparent magnitude in the y-axis and color index in the x-axis. Okay, so let's go to the next. So let's talk about the main content of this lecture is the data. So there are the different kind of surveys which happen in the past, and then they have all kind of archival data which they have stored. So for example, in the right hand side you can see there are the Gaia which usually pointed to the to observe the galactic plane to map the galaxy, our galaxy. And then there is the SGSS. So SGSS is mainly famous for imaging the sky and then getting the spectra. However, SGSS is slightly old and then it's still active, but most of the objects in there are only bright object. So their image limiting magnitude, which means how faint they can observe, is not at a good level. It's, I guess, less than 20. So, but in the spectral wise, so SJSS has lots of the spectra for the stars, quasar, AGN, and all. So, if you need some spectra for your interest of object, then SJSS is very good option. And then there is a two mass and WISE. So these both are for the infrared astronomy, and then they map the sky in the infrared range. And then again, so Panstar is again very good in the terms of the photometry and imaging. So it covered the all the northern sky, and then if you need a deeper image for anything you want to do. So for example, if you want to see the fainter galaxy and then want to study, and then or if you want to calculate the 0 point, for example, you want to calibrate your apparent magnitude with the into the calibrated magnitude, you can utilize the Panchar cataloger. And again, the Panchar is using the SGSS filter. Again, so whatever the object you are observing in which filter, according to that, you can choose which of the survey you can utilize for your calculations. So and then again, so ZTF is famous for the time domain photometry. So they are so lots of the data which are observed by the GTF are public, and then you can get the day by day data basically. So if you want time series of data, you can get that. Again, there are more other telescope, for example, CHFT and all. So they are also giving the time series data. I will talk about that. And left hand side, you can see we have a data catalog services. So these services are mainly utilizing the catalog, which are already there, and then giving you the services. So combining lots of the catalog and then making the complete sky, and then giving the uh, tables for from different catalog if you want to cross match or and do uh, more in the from the information combined from the different surveys. So I will go through one by one. So this is the CDS is the very good source, and if you want to, so this source is basically including all the data from different kinds of catalogs, and then also it is taking the data from the papers which is already published. So if you want to have some any data, any photometry and anything, so you can utilize this, and then for example, if I search this area and then is loading probably. Yeah, okay. So this is the something lots of the people I think already use the Aladdin, and this is famous and then map all this sky in optical band, and then uh, here in the catalog section we can see that with this particular coordinate are observed by the which number of catalogs. So for example, here we can see that the Gaia catalog, the Gaia in optical is there, and Tumas in IR is there. All wise is again IR infrared information. So Panchar is again optical. So lots of the catalog we can see that this particular coordinate is observed by these surveys, and then whichever we want, we can go to that and then find the useful information. We will do that, and then we can again see that the year wise. So this particular data is observed by how much times over the year. So that can also be seen here. So and then if there are types of the object and then famous object is there, so then we can also find the nearby object, and then this is our source. And then if we go to there, and then we can say this open up the symbol. I will go to that. Okay, and then again, so it's very important thing. So wherever the information it is getting from a different paper, so it is citing them. And then here you can see the photometry. So, sorry, spectrum. So this is a wavelength, and this is a flux. And then we can see that at which wavelength, with how this object has the brightness. And then these are, I guess, particularly coming from the photometry of the object at different filters. So there are two ways of taking the spectrum. One is if you're taking the photometry in the different filter, then from that you can make the spectra. And then other is taking the actual spectra of that objective. But that required the grid lens, grid to resolve the light into the different wavelength. Okay, so let's go to the one of the yeah, quick look. So in the quick look, we can see, so this is the example of the Gaia catalog, and then here we can see whatever the object we are in interest in, so we can utilize them. And so we have again, so as we discussed, we have a proper array deck of that objective, and then we have a source ID, and then we have uncertainties in the these two columns showing the uncertainty in the array deck or say the coordinate, and then here you can see the parallax angle. So it is in a milli-arc second. And again, if I'm correct here, I can click on, okay, so it is changing the table. So yeah, uh, I will show you. So there are the few catalogs we can fetch and directly in the especially in the visual query, and then here there we can also fetch the information what are the columns are showing. So let me show that. So if you click on visual query, it first go to the query part and then put the particular array deck from that page, and then also listing what catalog there you want to see. So here it's already automatically listed in the Gaia catalog, and then automatically listed the array deck from the that object, and then we just need to submit it. And then here we have a same table which we are looking before. And then if you want to check what the column is indicating, that you can see by one. So let me show something different. For example, this one. So so this is again, so this is showing the parallax angle, and then you can see this is in the milli-arc second. And okay, and again, so Gaia is very famous for having the very accurate value of the parallax angle, and then from there people can calculate the distance as we discussed. And then if you are finding very interesting object in our Milky Way, then you can find the distance using the parallax angle, and then find the properties of all that object. And again, Gaia has a few of the magnitudes in different filter. So it has a G band magnitude is again visible band magnitude. It's very wide and then in the visible range. And so again, it has a, BP magnitude. It's a blue filter basically. And so the magnitude here is indicating that how blue is the object as respect to the RP magnitude. So in RP magnitude is the filter in the redder side, and BP magnitude is filter in the blue side. And then combined from we have a magnitudes value. So for example, let's say take the one of the first example. Here we can see its magnitude in BP is 18.8, which is fainter as compared to the RP magnitude, which is 16.3, which is more brighter. So it means the object is more brighter in higher wavelength, and we call it the object is red. Okay, and let's come back to this page. So yeah, from this page we can access multiple catalogs as we want to, uh, and then so all kind of tables and all whatever we need to play with the tables. It is this is the best I would say best website. The Visual Query is the best one to look at. Okay, and then CDS has more multiple services. One is the Simba, and I guess Simba the people, lots of the people have utilized. And then my journey started with the Simba, so it was I also start look at the Simba, and it was the first catalog query for me in the start. Okay, so we have again, let's say this time 31. And again, so if we don't know the object name, and it can happen, and then we can put query it using the coordinate queries. Okay, and let's see the same one. And then again, so this is giving the almost similar type of information which we saw earlier, but mainly from this page we can see the again the right side is showing the Aladdin sky view, and then left side it's showing the name. If that particular coordinate is classified, then it will show the name of that object. And again, so it has a proper array deck. And again, I would say ki, currently we are using ICRS array deck because it's again, so this FK4 ICRS are little bit different because the Earth is recessing. So I will not go into detail, but better to use ICRS as a standard coordinate to communicate with others. Okay, and let's move to the one X match. So I found it very useful, and this is interesting in the way let's say it has a multiple catalogs which we can query. For example, let's say we queried SGSS, and then here we queried two mass, right? And then then we have to move for uh, the cone search. Otherwise, it will try to query both the catalog, and then it will take lots of the time. So considering the time constraint, we will do the cone search, and let's say we have again 152 as example, and then so it's at center you can either put some coordinate, or you can either put name of the objective or the any non-objective. Okay, let me put for the example, let me put some coordinate, let's say. I hope this will work. And so again, we have to be careful what are the accepted way of putting the array deck. So sometimes it usually these surveys accept all degrees, HMS in any format. And then let's say we want 10 arc minute object. So this is the cone search. We wanted this particular array deck at the center, and then want the region of 10 arc minute cone. And then let's begin the match. So now we can see here it is trying to cross match uh, two catalog, and then it will give you the CSV file. Okay, let's download it. If there is a cross match, then it will have some values. Right. So this is a here we download a cross match catalog from the two different catalog for a particular array deck, and then around cone search. So using that, for example, if you want to study a cluster, so similar kind of thing we can do. So we can put the array deck of that cluster, center array deck of that cluster, and then put the size of the cluster as a cone radius, and then we can have a cross-match CSV table from different catalogs. So here we can see that we have two mass and mm, this one, okay, this one, this one. So in 10 arc minute, so this one is the older one, so which I queried before, but this one is the current one. But unfortunately, within the 10 arc minute, there was no cross match between the two catalogs, and then that happened because SGSS has a little bit of limited catalog. It's not covering the all the sky. So yeah, there are the chances that LGSS might not have might not have covered that particular array. Yeah, so I just problem is probably with the SDSS. Let me change that. Let's say we use the pen star and search it. Okay, this is the last try. Yeah, so this is now very large catalog because I put the 60 argument. And yeah, so here we can see we have object ID from yeah. So in the start of the columns, you can see these are the information most mainly from the pen star, and in the end of the column, it's from the 2 mass. We have the information mainly from the uh, 2 mass catalog, and then it queried and then give you the so it so within the uncertainty region. So here again we can see that we put the 5 arc second uncertainty region. So we have followed that. So by position we what we constrained here that whatever if the two object is within the 5 arc second, then it is making it as a same object and then giving you the same uh, information for that particular object. So here is the cross match result, and then here we can see from the pencil we have all the magnitude from G to I. So Pancher has a G, R, I, Z, and Y. And then Tumas has a JK, GHK band, and then other band. Okay, so that is a example of a cross match. And last example from the CDS is querying the Bezier table from the Bezier. So Bezier is a very large catalog, and then again, if I query directly here uh, uh, without putting any catalog name, then it will give all the catalogs for that array. It's same as a CDS, but we can see that there are the different catalog and which is listed here, and then they have proper categories. And for example, we have a different category, for example, astrometry data, photometry data, spectroscopy data, and then other type of the objects. So let's say if we need a photometric data. So we queried it, and then we can see from the photometric data, it has all the category for the different surveys. And then here we can see that similar way that if we want to see the penchar, for example, so penchar has a probably a particular name. It's should be okay, we can search it better way. So here we can see there's a so this number is very important. I'm going to show that. But if I click here, then it will show the next page, and then here we can see it tagged that particular catalog, and then whatever the object name and the coordinate we will put, it will give the information specific to that one, and then only from the that particular catalog. And then why this number is important, I am going to show the how to fetch the similar table from Python using Python. So this is an example using Python. So Python has a extra query package, and then it queries everything. So and any cataloger, so they have all the API system, and then can be queried from the extra query. And then, for example, here we try what are the input we require is mainly the central array deck, which we used before. And again, if you have some constraint that you if you want a particular uh, magnitude in which you want to see the objective, that you can put. Otherwise, we can remove that. It's a choice. And then if even if you want a particular filter, you don't want other filters, you only want a particular filter, then that can be also be done with these filtration. So here we filter out that we require this range of the magnitude, and here we filter out we require the error in magnitude which should be less than zero point zero 0.05, and here we filter out the number of detection. So usually what we require is, for example, the photometric calibration. So we don't want force source to for the calibration. We always want a actual source. So the number of detection is very large. It means that this is a real source and then can be used for the calibration. So yeah, let me put so let's go with the Gaia, and then but Gaia will not perform the filtration for the filter because filter is wrong. So it will, so it is querying. So whatever the wrong filter you will put, it will just ignore that. But yeah, I'll check. So yeah, so this is the same information we are getting from the Python. So and again, so for the automation, these type of things are very important. And then I would encourage all the guys to go through the Python and then utilize this thing instead of web page. And it in the start it is difficult to go through the coding, but when you used to it, then it will be much better. Because even myself, I was I'm not using much of the web page. I'm using mostly from here because I can get the limited data and then directly work on my topic. Yeah, so the here we can see the similar type of details we have here, and then we can store it and in the CSV table and all, and then utilize it. Okay, so I have done the CDS part. I have, and then also give the example of the Python. I have little bit of more, but so far anybody have any doubt, and how much time I have?
Uh, Hello, sir. So, we started late. So, can we have for another 5 minutes, and then we will, because we have another program
Mhm.
with our account at 6:30. So
Okay.
at 6:15 we will end, and tomorrow, of course, we'll start in time, and again we can go up to 6:15 or so. So
Mhm.
my if my one of my suggestion here is, uh, tomorrow, of course, you'll be showing the examples, and you will be showing how to do the analysis and some part about, how to get the meaning out of whatever the data analysis
Mhm.
done.
Yes.
But
Mhm.
maybe either today or tomorrow, uh, because you said that some of the basic Python codes, if you can share that particular file, probably starting hands-on people may start. Of course, Python, many students will be already aware of. So there could
Mhm.
be some people who may not be aware. But then what we will do is we will, at by end of this, I will make an announcement that we already have our winter school lecture recordings available on our Wilson College YouTube channel as well as IIPT YouTube channel. So, how to use Python, pandas, and access data. Those lectures are already there, so students can see those lectures. And our aim here was, no, they start using these online archives and at least start with some simple kind of projects, because these projects really help them for writing. I mean, as a practice as well as for their SOPs, if they want to go for higher studies, also they become very useful. So that was our aim. Right now there is no chat here, so there is no question here. So can we use 2 minutes or 3 minutes to launch a poll
Sure.
on the feedback, and then we can continue tomorrow? Is that fine?
Okay, so let me give me just 2 minutes just
Right.
for the DS9. So I will show the DS9 tool, and then again I agree with your comment, and then I also plan to make the proper code. So for example, I will make the function so that people don't have to look into the code. They can just put the input and then get the output. They should know what is the input and then what is the output. And then if anyone interested, they can look into the code. But I will make the proper functions and then put the proper description and then share that code. So for now, I did not get the time to do that.
Yeah. Thank you.
Yes. So just so we will cover this one tomorrow because this is more searches from the uh, different catalogs, and for example JWST, HST, and all these catalogs. And but again, this will be covered tomorrow. Let's jump to the DS9. So I would like to cover one tool today, which is a DS9, and then I hope and few of the people have already done that, used that. So this is a one of the example. Okay. So we will go step by step, image display and image analysis. So first of all, this is displaying the image. So this is the observation which we took last night with the GIT, and here we can see that each point, each pixel we call it. It's a each pixel, right? Each pixel we have a proper RADX. So in the WCS column rows, we can see that each pixel has RADX. So that's how we convert from using the astrometry. We convert each pixel into world coordinate system so that we can have proper RADX over for each sources in this image. And and in the edit, we can go to any object if we want to. So, for example, if you want to search for particular object, for particular array tag, then you can just put that here and then apply, and then it will move to automatically move to that position. And if you want to search for something and all over the place and then zoom, and then you can just pan it and then utilize it at different positions. And let me give you the statistical analysis. Sorry. So for example, here we took the projection from the region. So we have different menus. So here we go to the regions and then go to the shape, and then by default it is a circle. So that's why I was able to make the circle in the image. But if I choose a projection, then you can actually make the, and again in the edit region you have to select the region, not pen, and then you can make a projection of a source. So this is the example that the projection over the source. So x-axis is the pixels and y-axis is the counts. And then it is basically is a physical PSF, you can say. And this is a PSF, so point source get spread out and then form a point spread function type source here. And then usually if you want to measure the brightness of this source, you usually fit this physical count with some a model or some PSF fit. We call it PSF fit, like a Gaussian or Moffat or any other numerical models. And then you can, if you fit the, let's say for if you fit the Gaussian, then you can immediately calculate the area under the curve, and then this will give you the brightness. So that's how the photometry works. Yes, and again in the shapes you can see we have different kind of options. For example, we have a ruler, and we can calculate from from one object to other what is the distance and all. So again, so here we can see that this is a something 59 arc second away from that distance. This is uh, showing the distance between the two objects. And then if we have a distance of that object, then we can find the actual distance between the two objects. And then again, so I used to make the the chart. We call it. So yeah, finder chart. So again, so we can make the finder chart using the DSNN also. So it has all the component. You need the compass, you need the ruler, and all the things you have, and then you can make it. And the other example is going through the frame. Let's say lock it to the WCS so that it will be north aligned. So here you can see that in actual we are observing the image and then it is in a different orientation. So if we wanted the y-axis, if we want a north axis at the in the y direction, then it will it oriented. And then it is very easy to compare with the catalog images because most of the catalog images comes with the north line in the align with the in the north directions. Yes, and one last thing I would like to show is since this is image is WCS solved, so we can actually overplot the catalog. So, for example, right now I'm going to the analysis and go to the catalog and then going to select optical catalog, and then we will check that each object is in the catalogs. So yeah, and here we can see that I open up the GSC catalog, and then this is again a catalog which was used by the made for the HST, Hubble Space Telescope, to pinpoint the object in the sky. So yeah, I we loaded it, and then here we can see that we have a bunch of the sources which is overloaded, and then in the edit you can select the cat and then here you can see this object is here, and then it is showing by the red. And then even you can do opposite. If you're clicking in the image, then you can check which of that object particular in the table. And then from the table, you can again get the information. So this JSC is mainly about the coordinates. So, but if you're loading SGSS or anything other any other catalog, then you can also able to see the magnitude and then other information which is in the uh, catalogs. Okay, so uh, so this just one last 1 minute. This type of image using overlay, we can also actually find the transient. So in this case, this is the actual transient. And you can see this one has no green circle. So this was a GRB which was happened yesterday. It's a 26A GRB, and then GIT discovered this GRB, and then this is the optical counterpart of that explosion which happened in the sky at this position. And first detection was by the SIFT satellite, and then they detected it in the high energy, which is a prompt emission. And then JIT was the first one which discovered its afterglow emission. So this is, and this from this way, and then there are the other way which we utilize. There are more scientific ways, for example, image subtraction, from which you can also find the new source. But and if you want to quickly search the things, then you can do the overlay and then find it. Okay, uh, and then last year, if anybody interesting, that we observed that currently trending comet, and just give me a second. Yes, and here we can see this is the comet, and then again the DSNN has the feature to lock the sources. So if I'm the sources with the physical, because this is not WCS solved, so I'm locking the source, and then and we can see anywhere I'm moving, I can see the all sources are moving in all the frames. So I locked it, and then again we can what we can do, go into the frame and then blink it. So here we can see that Atlas comet, which is we observed from one time to other, and then we can see the time series of that comet. It's moving with time, and that's indicating that it's a non-sidereal observation, non-sidereal object. Okay, and yes, I'm done, and thank you all. And then we will continue tomorrow.
Okay. We shall launch a poll, and I request Professor Kiran Polvankar to propose a vote of thanks. But so I first launch the poll, and Kiran sir, you can propose
Yeah.
the vote of thanks for today.
After the poll is over, or
No, the poll is I'm launching. Parallelly, you can
Yeah.
speak.
Okay, people can see the.
yeah, so it's my pleasure to propose this formal vote of thanks. I thank Mr. Vishwajeet Swain for taking out his time and giving this wonderful presentation. He has introduced to so many archives and ways to analyze data. I'm sure the students will practice this before coming for tomorrow's session. Then it will be more useful. And I also thank the audience, students and faculty members, for being present here and actively participating in the presentation. Thank you. Thank you all.
Thank you, sir. We will keep the poll on for another minute's time. So requesting all to submit the poll.
Okay, thank you, and then stop my screen share.
Yeah. Thank you, sir. See you tomorrow. And all other participants, okay, please complete the feedback and see you tomorrow at 5 o'clock.